Okay, this is section 9-3, geometric sequences and series, the first day. So this is day one. So our goal for today, our kind of essential question here is we're looking to see if we can recognize, write, and find nth terms of geometric sequences and find the sum of both finite and infinite geometric sequences. So what we're hoping to do in this first day is answer the question, how can I recognize them, write them, and find the sums of them? So we're going to look at all of those different things in a geometric sequence and series. So we know a little bit about arithmetic. We know in general about sequences and series now. Now we're going to talk about this very special kind called geometric. So we're going to go ahead and add this example in. So we're going to talk about a good example of something that is geometric to get you kind of the background a little bit on what these kind of sequences look like. So we have 2, 4, 8, 16, dot, 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 keeps going. So we'd be looking for how do we get from one term to the next. Now, if we were thinking arithmetic, we'd be looking for a common difference, like what are we going up by that's constant each time. So you might think, oh, I'm going up by +2, but that doesn't work when we try to go to the next one. We're not adding 2 there. That would have been a 6. So there must be a different rule or pattern to get to that next term. And actually, I think most of you probably can see that pretty quickly. Another way to get from a 2 to 4 is times by 2, and then we can times by 2, and that works again, and times by 2. So we can actually talk about this as a multiplication factor from one term to the next. So multiplying by 2, if I want to find that next term, it would be 32, 16 times 2. So this is actually a great example of a geometric sequence. If I multiply by something to get to the next term, that would be a geometric. Now, if I wanted to find the 25th term, we have to think about how would I do that? So, I mean, I could keep going, right? And I could keep doing this times by 2, but I would hope that there'd be a way that I could get to that 25th term. And we're going to talk about that in just a moment. What would we be looking for? How many times would you have to multiply by 2 to get to that 25th term? So we'll think about that, and we'll come back to that when we talk about that nth term formula. So a geometric sequence then is a sequence where the ratio of consecutive terms is always the same. So there's a common ratio. So the ratio of consecutive terms is the same. So if you take any two consecutive terms, so that's terms right next to each other, like term 3 and 4 or 4 and 5, and you do their ratio, you'll always get the same value. In other words, you're multiplying by the same thing each time. And that same thing that you're multiplying by, that's that common ratio. So we use the letter R for ratio. It's the ratio of consecutive terms. So it's the number that you're multiplying by. If that ratio is less than 1, that means your terms would be getting smaller. If the ratio is bigger than 1, that means those terms would be getting larger. So it's a ratio of consecutive terms. We'll also talk about what if it's negative and what impact maybe would that have on your terms. So we'll use this common ratio of R. So let's think about how we would check to see if something is in fact geometric. So we'll see if that is the value that we're going to have. So let's take a look at this one and see if we think it is in fact geometric. So we're starting with a 60 and it goes to a 30. So if I take the 30 divided by the 60, that would be a 1/2. So if I'm checking to see if this is a common ratio, it looks like I should be multiplying by half. But then that same ratio should work for the next one. And 0 divided by 30 is most definitely not a half. So this is definitely not a common ratio situation. So this is definitely not geometric. Now I bet a lot of you can guess what it actually is. If you look at those values, what are you doing each time to get to the next term? Well, it looks like you're going down by 30, right? So if I subtract 30, if I subtract 30, subtract 30, and I could figure out what those next numbers would be in the sequence. So this one is actually an arithmetic. So it's the type that we were looking at in the previous section. So it was a common difference, actually, not a common ratio. So we do need to be able to tell the difference between what kind of ratio we have. So let's talk about those terms, and we'll go back to that intro example that we did that was geometric. So if we're going to try to find the terms in an arithmetic sequence, I'm going to start down here with how I would write the terms. I'm always going to be starting with the first term, which remember what's an A with that subscript. To get to the next term in the sequence, what would be the A2? So I'm going to kind of write this both ways. So the second term in the sequence, you're going to be multiplying the A1 by whatever that common ratio R is. So it would be A1 times R. Now, if you're going to get to term 3, well, you're going to have to multiply by that ratio again. So can just take whatever A2 is and multiply it by the ratio. But if I go back to thinking about it as the term 1, that would be A1 times R, which would be A1 times R squared. In other words, I'd have to multiply by the ratio twice to get to the third term. How about term 4? Well, I'd have to multiply by R again. So that would be A1 R to the third for term 4, and so on. So now let's think about what that would mean for a n. Okay, so if I keep going in this list, dot, 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 and I want to get to the nth term, like the last term in the sequence, or a particular term at the end, how many ratios would I need? Well, for term 4, I needed 3 terms, or ratios. For term 3, I needed 2. For term 2, I needed 1. So for term n, I would need r to the n minus 1, one less of those common ratios. Why is it one less? Well, same thing as arithmetic. We never need one for the first term. It's only for each subsequent term afterwards. So the nth term formula for geometric is an equals a1r to the n minus 1, one less of those common ratios. So if I go back to that intro question, how would you find the 25th term? Well, you would take term 1 times the common ratio to the n minus 1, so one less. So our first term was a 2. Our common ratio was also a 2, and I would be going to the n minus 1. Well, n is 25. That would be to the 24th power then. So it ends up being whatever that value is, which is awfully huge. So actually 2 to the 25th altogether. So big number. But we can actually figure out what that number is down the line. It's always one less than your number of terms. All right, so let's try a couple and see how this works for us. Can we identify and see if something is actually geometric? And if it is geometric, can I find specific values in that? So here's a checkpoint question. So there's a video. Find the formula for the nth term of a geometric sequence. So they're telling you that this is geometric. Let's see if we can figure out what your common ratio might be. So to figure out a common ratio, remember you take any term and divide it by the term in front of it, consecutive terms. So either 20 divided by 4 or 100 divided by 20. Either way, it should be in common. In other words, the same. That means the common ratio is 5. So we're multiplying by 5 each time. So how would we write the nth term formula then, just in general? Think of it like writing the rule. So an is equal to a1 r to the n minus 1. So the an would be the first term, which is 4, times the common ratio, which is 5, to the n minus 1. That's our equation, which models all the terms in the sequence. Now, notice what kind of equation this is. Where's the n located? It's up in the exponent. So these geometric are like exponential equations. They're just like our exponentials we studied earlier in the year. So when you think about an analogy, linear is to arithmetic as exponential would be to geometric. So it models that same sort of behavior. So now we want to find the 12th term. That just means that n equals 12. So if I want to find a sub 12, it would be 4 times 5 to the 12 minus 1. In other words, I need 5 11 times. So I would need to multiply 5 to the 11th and then multiply that by 4. So whatever that term would be, that would be the 12th term in the sequence. So that's 195,312,500. So big value. These, when they grow exponentially, they're going to get pretty large pretty fast. So expect some numbers that are either really big or really small when we look at exponential growth and decay. All right, let's try a couple more here so we can talk about a different way to get from one term to the next. So that was a model or an equation. Now we're going to talk about the recursive version. So we've talked about recursive formulas before. That's where you use a previous term to find the next term. So we need to know, say, A7 to be able to find A8, or we need to know A100 to find A101, which is convenient if you know that previous term, not so much if you don't. Like if you're going to jump ahead and find a term later on, the AN formula is usually a lot handier. But if we want to find this recursive, all we have to do is multiply. So we're going to take that previous term and just multiply the AN by your common ratio, so by that r, so then we get that next value. So the n plus 1 term is always going to be found by taking the an and multiplying it by the ratio, because that's how we get to the next term, right? We multiply by the r. So the reason they're asking you for this or talking about this is that's a way that you can find next terms in a sequence. So whatever term you're starting with, in this case it happens to be term 1, we can find the next term in the sequence, the an plus 1, by just multiplying by the common ratio. So my common ratio ratio here is the r. So I'm going to multiply by -3 to get to the next term. So that would be -15. And then I could multiply by -3 again. That would give me +45. Notice if your common ratio is negative, your signs do alternate. So it's very interesting. You're going to have alternating signs for these. So they want the first 5. So let's go ahead and keep going here. So we'd multiply by -3 again. So that would be -135. Notice the alternating sign. Multiply by -3 again would be +405. So we could keep going, right? We're going to keep having those terms. Now, that works great for like the first few. If you want to find A12, you can literally keep doing what we just did. So you can keep multiplying by -3 until you get to the 12th term. Takes kind of a long time. It might be a little bit easier to do our AN formula for this, just because it's a little bit more efficient. So the A1 R to the n minus 1. So it might be a little bit faster to think of it that way when we do that calculation. So that would be our first term 5 times -3 to the 11th. So go ahead and try typing that in and double check your answer. So again, it's going to be pretty large because we're going to be doing that exponential growth. So it's going to grow pretty quickly. So we have recursive, so taking the previous term to get to the next term, multiplying by the ratio, or we can use our AN formula, which we can find a specific term pretty quickly. So we have some options. We have some tools in our arsenal here. All right, let's try another one. So it says find the 8th term of a geometric sequence that begins with 15 and 12. So our sequence starts with 15, comma 12, comma dot, 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 and I want to find the 8th term. So you're looking for A sub 8. All right, so go ahead and pause and think about how you might approach this. What are your options? What do you think might work to find that 8th term? And then we'll talk about some options together. All right, well, one way you could approach this is, since we could figure out the common ratio from this, I think either way we're going to need to know what we're multiplying by. 15 going to 12 means it's going to be multiplied by whatever 12/15 is, so 4/5. The numbers are getting smaller, so it makes sense the ratio is less than 1. They're going down, decay. I could just keep multiplying by 4/5 until I get to term 8, and I could keep doing that and life would be good. It would be absolutely fine. I'm not sure I really want to write out 8 numbers, especially if they're fractions, because they might get kind of small and kind of gross. So I may be more inclined to use the AN formula, the A1R to the n minus 1, because it might be a little bit more efficient. So my A1, that 15, my ratio is 4/5, and I'm going to raise that to the 8 minus 1 power, or 15 times 4/5 to the 7th. Now, depending on how precise you want your answer, you can do the 4/5 as a fraction, and you can write that out in the fraction form. So that's 245,000, I believe, 760 over 78,125. Some people are like, you know what, an approximate is good enough. 3.1457, etc., etc. This really becomes a matter of preference. What is the easiest way to have my answer? Do I need an exact answer, or is it okay to have a rounded answer? And that's really a conversation for what you'd want to be doing with the number. But in terms of efficiency, I think using the AN formula would be the fastest. All right, let's try another one. We're just, again, trying to identify, how do I know if I have a geometric sequence, and then how to find the other numbers. All right, so let's see what we know in this one. It says the second term of a geometric sequence is 6. So I know that A2 is 6. It says the 5th term is 81/4. So A5 is 81/4. Find the 8th term. So what you're looking for is A8. And it says assume all of the terms in the sequence are positive. What that means is that your common ratio is going to be positive. So we don't have to worry about the plus or minus. We know that all the terms are positive. All right, so what we really have then, we have an A2. I don't have A3. I don't have A4, but I know A5. Oh, don't need a blank there. I've got that one. So A5 is 81/4. So this is the 5th term. I don't have 6. I don't have 7, and I want to find 8. So sometimes I think it's helpful to visualize and think this way, so we can talk about what values we have. All right, so I think what bothers people in this one is you don't have an A1. You don't have that first term, but really any term in your sequence can be assumed to be like your starting term, so your initial term, and then any term in the sequence can be like your final term. So I want you to kind of direct your attention to this part of the sequence. I really can think of the sequence as 4 terms. So I have 1, 2, 3, 4 terms. I have a starting term and I have an ending term. So think of your AN formula. I know we often use A1, right? We have to think about like term 1, but what if we start at term 2 as our starting term and we end at term 5? So we still have a starting and a final. I think we know a lot of that information, and what we need to really get from this is I want to be able to solve for the R. If I knew the ratio, I can find anything I want. That's really the missing link here. So if I have two what we would call non-consecutive terms, anyone can be the starting term and anyone can be the ending term. I can solve for the ratio because I know what the n is for that sequence. How many terms are in that sequence if I go from term 2 to term 5? Okay, so our n then for this sequence, we would have 4 terms. So if we start at A2 and go to A5, that would be to the 4 minus 1 power. So again, the starting and the final, it doesn't matter if you have a term 1, it's just how many total terms you have in that sequence. So if you're starting at term 2, going to term 5, that's actually 4 different terms in that sequence. So we can solve. We can solve for r, and then we'll be able to solve for any term that we need to. So we're going to solve for r, and that would be cubed. So we're going to be solving for r to the third. All right, so think through order of operations. You would want to get rid of the 6 first. We could divide by 6, but it might be easier to think of multiply by the reciprocal. It might be a little bit easier way to simplify that. So r cubed would be equal to, if we simplify that down, that would be 27 over 8. And then to get rid of cubing, we're going to cube root both sides. So cube root of 27 would be 3, cube root of 8 would be 2, and we would get our r. So now we know what we're multiplying by. So we're multiplying by 3 halves each time. So we know what our common ratio is. So we have lots of options now to pursue here to get to the A8. We can go back and we can use either the A5 or the A2 as our starting term, right? Use our AN formula again. And remember, it doesn't have to be A1. It just has to be a starting and an ending. So I know we don't have term 1, but we don't really need to find that. We could use A5 as term 1, or we could use A2 as term 1. Or since it's only 3 terms later, what some people will do is they're just going to multiply each time by 3 halves. So we multiply this one by 3 halves to get to A6, multiply by 3 halves again to get to A7, or multiply by 3 halves 3 times to get to A8. So you could really do it separately too if you wanted to fill in the blanks in the middle. I'm going to think of the AN formula to get directly to term 8. So if I wanted to use my nth term or my n term as 8, I'll probably use the A5 as my starter, just a little bit closer than A2. And again, we can figure out what that n is for that because we know we have A5, A6, A7, A8 is a 4-term sequence. So I'm trying to figure out term 8. I know term 5 is 81/4. I know my ratio is 3 halves, and I'm going to raise that to the 4 minus 1 power. Now, if you take a look at it, that would be cubed, right? So 81/4 times 3 halves cubed. So when I do the 3 halves cubed, take a look and see what that means. That means you're going to multiply by 3 halves 3 times. Well, yeah, of course, that's exactly what it'd be if you multiply them separately to get what those values would be. So the 8th term then, if I do my simplifying, I'll do it as an exact, would be 2187 over 32. So I have that 8th term. So the whole idea with recognizing a geometric, remember, is we're looking for something that the common ratio is the same. So what you multiply by to get from one term to the next is always the same value. So you're multiplying by what we call a common ratio. So being able to find terms in the sequence and find a particular term is what we're looking for today. So the day 2, we'll talk about how to find the values of sums. So finding finite and infinite sums. So the assignment for today is just on finding particular values. So it's these, and I'll scroll down so you can pause, and those, finding a particular term.